Hey guys, welcome back. Today's lesson is on graphing the sine and cosine functions. And what we've looked at so far is just the relationship, like how to find the sine and cosine based on the unit circle. But if I want to actually graph it on the xy plane as its own function, for example, if the x-axis represents the angle I'm at, and what will the sine value be, aka the height, that's a separate function than if I consider the cosine its own function, and we'll talk about that. Today's mindset message is, find the beauty in math. I introduced that in this topic because trigonometry has so many really crazy connections to other areas of mathematics, and to me that's very beautiful. I love when things are interconnected, especially when things connect that you maybe wouldn't expect to be connected. We have two learning goals today. The first one is relate the motion of an object around the unit circle, that's the theme we've been doing the last few lessons here, to the sine and cosine graphs specifically. So we've talked about how they relate directly to the values of sine and cosine around the circle, but we're going to look at the graphs, and then of course sketching sine and cosine graphs. Today's lesson is really focused on just the basics of those graphs, and in a later lesson we'll talk about more complex graphs and shifting them around and stretching and things like we've studied in the past. Based on that, though, it is going to be important prior knowledge to think about remembering transformations of graphs when we've studied those in the past, and then, of course, being able to find sine and cosine values from the unit circle from before as well. Let's take a look at a warm-up example that has to do with graph transformations. So right now I gave you f of x equals x squared, so just the basic parabola, and we ask, how do the following graphs compare? So this is one where you can look back in previous notes or something if you'd like and pause it, but you may also want to just jump ahead with me right now and just talk it over as well. So let's go ahead and take a look at that. Okay, so I actually altered one little thing because it'll just help me with the table here. So actually we'll do f of x minus 2. Okay, so first of all, remembering what this means, since x squared was my function, then x minus 2 all squared is what this is, right? And then for f of 2x, then it's 2x all squared. So essentially what we're saying is, if I were to take every input and double it, right, what is the overall effect in the graph? And here it's saying if I take every input and I subtract it by 2, what's the overall effect in the graph? You don't necessarily have to write this part and this part down. It's a little bit of the background to remind you of why it is the way it is, but at least you can just write the answer down afterwards anyway. So one thing to connect here is, let's start with this one. I want you to notice that these outputs have a connection here, in fact, is that the regular outputs for the original function compared to these outputs are just shifted. If I kept going up this way, I'd get this 9 and 16 up here, right? And of course, if I kept going down here, then I'd have 1 and 4 again. So essentially what we're saying is, these inputs create the same outputs as if I shifted them down, up by 2. And what we're saying then is, it's essentially going to give me the same outputs, but I've shifted up, right? And that means on the x-axis, that means I've shifted to the right. So the main answer to this, and you may remember this is shifted right to units, okay? So normally x squared is at the origin, but now it's just has its vertex shifted to the right 2 units. And we can come up with a similar logic here, although it's kind of a little bit different here. You notice that actually if you look carefully here, each of these outputs is multiplied by 4. So it's tempting to want to say, because right, the minus 2 here makes it feel like it should be shifted left because minus means left, but it's almost like we're having to counteract that minus 2 by adding 2. That's how I think about it. So anyway, that's right. This one, you may think that multiplying or doubling all the inputs means that the graph is going to be stretched out, doubled in x direction, but it actually does the opposite. It actually shrinks it in the x direction by a factor of 2. But also you can think of it as stretching it, in this case, stretching it by 4. Notice they all multiply by 4. So, however you want to think of it, but since this was directly attached to x, it's going to be We actually will say often compressed by a factor of 2. And so how it would look in comparison would be that it is more stretched out than the original one. So if this is x squared, this would be 2x squared. So conceptually, all I wanted you to do is remember those things because we're going to end up applying those. Now let's go on and actually take a look at the graphs of sine and cosine.
So here's how we can construct the sine graph, the graph of the sine function. Imagine we have Paul here walking around the track still, right? So here's our unit circle, but what we're really trying to track here, no pun intended, is on this xy plane. We may actually, instead of calling this the x-axis, it would be good to think of it as the theta axis, right? The angle. So every angle around the unit circle is represented as you move along here. And what we're going to track here and put as our output is going to be whatever the sine value is when that point is at that angle on the unit circle, right? So the highest you're ever going to get on the unit circle for sine, or cosine actually, but is 1. And the lowest you'll ever get to is -1. So let's go ahead and start moving around. Watch when we move this point around. And right here we're at 37 degrees, let's say. Let's just stop real quick. What we've tracked so far, all these blue points are all the possible sine values, aka the y coordinates of this point P as it moves along. And this is tracking them out. Currently at 37 degrees, our height is at 0.6. Now I want you to think about something here. We're going to move up and get to a highest point, but then this 0.6, he's going to have an exact match reflected over here in quadrant 2. So watch what happens when we go and watch what the graph looks like, the blue graph. I'm about at 90 degrees right now, so it means I reached the highest point. And then as I keep going, remember how we said there's always going to be a match on the other side, right? And as I get to 180 degrees, there's some symmetry here because we've essentially matched the behavior when we were going up as we went around. So it went up and then down in a symmetric way. And similarly, quadrants 3 and 4 are going to have sine values that exactly reflect each other, but they're all negative. And so it turns out the sine graph looks like a nice wave like this. And then of course, this doesn't let us do it, but we could let it continue on. And it's interesting that it's going to actually repeat itself. If we kept going, it will just repeat that same wave. And actually, even if we went backwards, it would do the same thing. So that's what the graph of sine looks like and why it looks like that. And I'll put this link up for you to play with yourself if you want to. Now let's look at cosine. This one's interesting because at Paul's initial position, he actually starts at an overness of 1, right? Remember the cosine goes with the x-coordinate. And this is what's a little bit confusing when we look at the graph, because remember this graph, the x-axis now of the graph represents as the input, in this case what we're going to consider the x-coordinate. You could also just call this theta, but the input here actually is the angle. So as the angle increases, how is this overall value of the overness, aka the x-coordinate, how is that measured? So even though this is technically vertical, it just represents the actual value of the overness within this graph, if that makes sense to you guys. So we're actually starting out at a value at an output of 1 because the cosine is 1 at 0 degrees. And as we move along here, cosine symmetry is going to be a little different because he starts up there, and you'll notice that this will then have an opposite type of mirroring down here instead of a cross, right? So up here, this looks very similar, but this one's positive and this one's negative because we went from a positive x-coordinate to a negative. And then if I just keep doing this, you'll notice that this third quadrant has some symmetry here. So our symmetry in this graph is kind of based around 180 degrees, I guess. And then we finish off. Now this looks really similar to the sine graph, actually, because the shape happens to be identical. But technically the values, the output values, start at different places for sine and cosine. And so what we can view them as is actually a shifting of each other on the coordinate plane, which we're going to take a look at next.
So now that we've had a visual of why the shape of the sine and cosine graphs looks the way it does, let's take a look at it in terms of radians. In our little demonstration, we looked at it in terms of degrees, but now that we've realized there's a direct correspondence there, we can map these in radians as well. So just another visual here for you, color coding wise. Remember that, let's just say Paul is going around the track and he's at something with some coordinates a, b. Well, if a represents the x-coordinate, which we know represents cosine, and if our angle is theta, then that means this is cosine theta, and b is the height, which represents sine, right? So this would actually be sine theta. Then we actually have the two functions, a equals cosine theta, and b equals sine theta. So I've actually color-coded those for us as well. One really important thing to remember when you're actually sketching by hand the graph of these is, I call it the 5-point rule, okay? And these 5 points right here along the x-axis will form the core basic shape of either the sine or cosine graph. And that would be 0, pi halves, aka 90 degrees, pi, or 180 degrees, 3 pi over 2, which is 270, and then 2 pi. And that's because those are the values where sine and cosine either reach 0 or their maximum or their minimum. And for the sine graph, we know he starts at 0 and then reaches his maximum at 90 degrees and then crosses at 180 and then finish that off here. And then for cosine, remember cosine starts at a maximum actually, since he's mapping the overness, and so his thing looks like that. Okay, so this should be another nice visual connection there for the graphs. So let's take a look and talk about some deeper connections between these two graphs. You may have already noticed this, but you can see that if I either shifted the cosine graph to the right, and how much is that to line up? Pi over 2, right? So if he shifts to the right pi over 2, then it's exactly equal to sine. They're the same exact graph because they behave the same, they're just offset. And the same deal goes, if I take the sine graph and shift it to the left by pi over 2, then it lines up exactly with the cosine graph. And this brings us to a very important thing that we're going to see recurring throughout our study of trigonometry, and that is what we call trig identities. And I do want you, as it says here, to devote 1 page should be enough in your notes for writing down the various trig identities that we develop as we go through this course. So we have some trig identities we can say right now, actually, and we'll remind what an identity is here as we go along too. Remember how we said if I took the cosine and shifted it, it would be the same as the sine? So what I could say is that sine theta, I could also use x, that's fine, but sine theta is the same as cosine of theta, but we said shifted to the right by pi over 2. And remember, it does the opposite when you're representing shifting, so it's going to be minus. To move to the right, I subtract pi over 2. That's an identity. That just means it's an equation that's always true. So this and this are replaceable for each other, always actually. And furthermore, we can do the same thing, but we can represent cosine as a shifting left of sine. So cosine theta equals, why don't you pause real quick and just fill this one in, and then we'll do it together. Okay, so this represents the sine graph, but shifted to the left, and that means it would be theta plus pi over 2. So these two go hand in hand with each other, and they go really well together. There's two other identities that actually we can say here that instead of relating sine and cosine to each other, you can say they relate sine and cosine to themselves. If you just only looked at the sine graph, let's say, okay, the purple one, how far would I have to shift him to get all the way to another maximum, right? Or you could take any point. I guess I could start here. If I wanted to shift this point right here until it overlaps with himself completely again, how far would I have to go? Well, you'll notice, if I shift him to here, it's not going to quite work because it's going up. I have to shift this point all the way 2 pi to here before it completely overlaps. So a really important property of both sine and cosine actually is that sine theta will always be brought back to himself once we've gone around a full rotation. But that makes sense, right? Because we saw that once this point goes around exactly one rotation, 2 pi, then we just repeat and restart where we started. So this can be expressed by saying this. And the cool thing is I could shift it left or right by 2 pi, and it's just going to become himself again. So that's what this is saying here. If I shift sine left or right by 2 pi, it will line up back on himself again. So it's going to be equivalent. And the cool thing is we can do that for cosine as well. The exact identical identity there, but with cosine instead. And that's really important because this is going to bring us to our major definition for this lesson. Let's look at that definition.
Okay guys, so now we get to kind of the culmination of this lesson with this definition. And the sine and cosine functions are probably the best examples of these type of functions. So we define a non-constant function f to be periodic if there exists a real number p such that for all x, f of x plus p equals f of x. And if you think back to our warm-up today and you remember the first one in our warm-up, when you add or subtract a value here with the input, it shifts the graph either left or right. So since we just talked about how sine and cosine can be shifted, in our case by 2 pi, and then they'll just overlap with itself again, it has this interesting kind of cyclical behavior to it, and that's what we call its period, right? So the period for sine and cosine is 2 pi. And so that value p, the smallest possible value, I guess I should say, before it overlaps with itself again, is what we call the period. Okay, so the key idea here is this right here, f of x plus p equals f of x. So essentially this means that the graph of f of x shifted p units left or right will line back up on itself, and sine and cosine are periodic functions with period 2 pi. So happy math, and we will see you guys in the next lesson.